worry about sharp pornography. So let's hope it's true. Any comments? More comments on that?
I mean, on the positive side of peer-to-peer, you have the whole ability to circumvent the like proprietary platforms. Like, I mean, I think the whole time, the whole sort of rise and plateau and hopeful decline of the .NET platform was really just such a incredibly poor platform that was, marketed to large companies, that got people working on these very large projects with really terrible technology, and really not forward thinking at all, and just completely proprietary. And having P2P means really getting away from these centralized monolithic servers that are platform, that are vendor proprietary.
Yes.
In a philosophical sense, one of the reasons that peer-to-peer is attractive is because it provides us with freedom against oppressive regimes, and that's a scale. So we've got properly oppressive regimes, and then we've got our own governments that like to spy on us and our activities, which is not pleasant, So that's one of the attractive things about peer-to-peer. So what we're doing by enabling peer-to-peer technologies is giving back freedom to the population. But if we start to get too hung up on how people might be using the service, then we effectively become almost as bad as the regimes we're trying to circumvent, because we're then interested in controlling other people's behaviour.
Of course.
So, with freedom comes costs, but freedom has a higher value in itself. Yeah. So I think that
without freedom of expression, you don't have democracy. Yeah. And without democracy, remember that.
Yeah. So there will always be evil.
Yeah, of course.
There will always be people that are inclined towards these things, and it's not something that we ought to get too hung up about, because we can't control.
But
if
so
we do,
every time I invent something, before I publish it, I think it will at least be more good than bad. And twice in my life it has been more bad than good, and I haven't published it. I drew it back. And actually, for instance, this Internet in Tanks project, it was delayed 2 years in Europe or something. And I still can't really accept that fact, because there must be other guys that know what I know, but they couldn't find them. And I talked with other guys in Sweden that I know, and they hadn't even found them, because they're hackers. I'm actually not a hacker, but I spent 10 years in a computer club, surrounded by some of the best hackers in the world. Because I kind of learned a little from them, at least. But so they had managed to find those guys. So sometimes you can't stop it, but you delay the bad things happening. So sometimes I think it's good to not publish technology that might do more good than bad. But as you say, freedom of speech is so vital that we have to have it no matter the cost. So it's nice to know that something that we thought was a cost, even wasn't a cost. Probably child pornography part wasn't a cost. Actually, it might be a good thing. And the terrorists we can't do anything about anyway. They will communicate anyway. So really, those two main costs that people are talking about, they aren't costs. And then I don't know if there's any really bad cost left. A little pirating of files, that's not especially bad. It's not a high cost for getting freedom of speech. That's a very cheap cost, I think. I think you think that too, right?
Yeah, that's right.
There's other ways to finance, to pay our artists their salaries.
The erosion of that business model has been happening for a long time with all that peer-to-peer, and they need to figure out how to deal with that themselves. It's not happening.
We can't give away democracy to give them their salaries. That would be ridiculous. I'd rather have a slightly higher tax and just give them their salary from our tax. That works too. That's simpler. We actually do that in Sweden anyway. Most of the artists are government financed anyway. But most movies are government financed in Sweden.
And now nomadic Arabs also have good broadband, which is awesome.
That's not bad. Yeah, so okay, that was a little about the peer-to-peer ethics. Actually, I'm almost ashamed to admit it now, but I spent 6 man-months on investigating that, because I really wanted to find the answers and speak with a lot of people, so I wasted a lot of time on it. But, So we're going to look at broadcasting perhaps a bit more. Yeah. Different kinds of broadcasting. If we have a chat room, which we of course should connect as a small world network with TCP connections, because a normal chat room with just, let's say, 15 members, then every node can connect to every node. That's the case. Everything we say can immediately be transferred to the other node. But sometimes there's hundreds of people in the chat room, or more listening and some are speaking. Then we can't connect everyone to everyone directly after a small world network. And then, of course, we will use the fastest kind of broadcast we have. When a node gets a message, it immediately broadcasts on all links. That means, for instance, this node will receive the message on all 3 links, or receive it on 2 of them and send it on the 3rd. And sometimes these 2 nodes will send the same message at the same time in both directions, and will end up in the queues for a tenth of a second later, so they won't know that they are saying the same things. But that's wasteful, but it has to have the speed. But when it's just humans chatting, that's not a lot of bandwidth. So that's what I call fast broadcasting. Inefficient, but fast. The opposite of that is what I call slow. What did I call it? Slow bandwidth with efficient broadcast. And it works. It's actually the original kind of broadcast. We called that gossiping in 2003, but that name has changed meaning now. So basically, if this one node is publishing something, a larger message, it sends it to all of its neighbors immediately, because that's the first step. They obviously can't have it. But this node won't broadcast it on. Instead, it will just send a very short message telling, I now have message number this and this. So a small identity of that message, like a hash or even shorter. We can make it even shorter. So it just tells this node, I have this if you want it. And this one might get that from both of these nodes, but not from that one, not at the moment. And then you can simply ask one of them and download it from one of them. And I mean, it takes a little extra latency here before it happens, but it costs you much less bandwidth. And this is especially useful for large things. But also fairly small things, you can still save a lot of bandwidth. And it's especially useful if, for instance, sometimes you don't only want 5 connections. Some cases you have 20 or 100 connections, like BitTorrent swarms. The more connections, the better, kind of. So then sending the packets over all those connections would cost you 100 times more bandwidth. So BitTorrent does exactly that. It tells, I now have this block, do you want it? And then you just get it from one of those that has it. So that BitTorrent swarms use slow, bandwidth efficient download. So it's slow in the sense of latency, but not slow in the sense of throughput.
So in a BitTorrent swarm, does a node announce to every other node basically in the swarm, I have this block?
To all its neighbors, not to whole swarm, just to its neighbors, just so that those is connected to. So it has a list of it has 2 ways of telling. If you get one packet, you say I have this packet. Whenever now it sends the whole list, all the bits 1 or 0. I have which packets it has of the entire file. So that's actually the same thing. But you can also use it even if there they have a preset list. They have that specific torrent. But you can also do it for new messages, of course. This node might have an ID for node ID, and then when it creates a new message, it's just a message number. How do you write a number in short form in English? NO or NOR?
Hash symbol.
Yeah, hash sign. Yeah. And that can actually be I'll tell a bit later, but that can be 2 bytes and that can be 2 bytes. So all you send to your neighbor is 4 bytes until I have this message. And if that one doesn't have that number, it just requests it. And the requesting it is also perhaps 4 bytes, just sending a response on. So you can have one header and all these are requests and then which messages this might want. So you can fairly efficiently do that. Of course, that costs some bytes back and forth. So if the message is really short, then don't waste sending that. Instead of just send the message immediately, because that's more efficient. So you have to have some logic to decide when to send it and when just to offer it. That also means that short messages will spread faster across the network. And that might be good in some cases, but that's just a side effect. So that's 2 kinds of broadcasting. And so chat networks should not use this, but file sharing uses that. And also mini groups uses that. If you have that, mini groups was when I connected all like 1,000 nodes together in one swarm, and all those 1,000 inside to spread out the data about what files they have. They should use this, because otherwise you will get all those thousands and thousands of file names from all directions, and that would be extremely costly. It also means, for instance, if let's say we have this node for some drops the links, for instance, because it disappears. And then to repair this stuff, it gets, for instance, a new link that way. That means those two nodes can tell each other what messages they have and don't have. For instance, it can tell, I know these nodes, it can send a list of what nodes it knows, all the IDs, just a list of that. And for each node, it can tell the max number of messages it knows. So for node number 5, I know messages up to number 25. So that means if it's 1,000 nodes times 4 bytes, that's 4 kilobytes. And then this node knows exactly what this node knows in the other one, 2. And then this one can see that it has up to message number 25, but I have the 26 method for that node. Then you can send that little offer. I have message number 26, do you want it? Instead of just sending all this, I have all these, do you want all of them? But that's silly, so we just count upwards. Of course, that means you might not have it continuously, so you have to have a little handling of that, but you can pretty much tell up to this number I have. And all over that is unclear to offer anything you have there. And you can improve it if you're smart a little more. But in that way, you can very efficiently just transfer what you need to transfer. Any questions about that? There are some more optimizations here.
How would you handle collisions in a situation like that, though? If you're having a chat room and then on one end of the network, a message ID 26 is sent, and before it reaches the other end of the network, another message is sent.
Because the node has a unique identity. And then inside per node, there's a unique message. So each node has a message number 26.
Kind of like a vector file.
Combined with the node ID. I like to make it bandwidth as efficient, so I only use 2 bytes IDs normally. But that's too short. So usually what I do when I connect a node, it will first broadcast its full name, all of that stuff, because you only do that occasionally. That happens just very rarely. You broadcast that over the whole network. Then in that it can allocate one of the 3 IDs. And if another node at the same time allocates the same one, they can go back and try again with a new identity. So they can collide. So before they start actually using it, they wait a minute or so, and then they see if it's still only I got it. If it collides, they go back and try again. There's some different approaches to do that. Actually, there is another approach to do that we use in teletext systems and other old school systems in the 80s. This ID isn't node unique. It's not unique to the sender node. It's unique in each connection. So when I broadcast a full identity, the full name of a node here, I add it as node 20. I call it not node. Let's say 15. So in that direction, that is node 15, and this will learn that when he talks about that node, that's node number 15. And in the other direction, the number 15 might be taken, or it might be number 27 in that direction. So you allocate it in both directions. And you do the same for all links. It might sound messy to do that, but it has a really simple code. It's just arrays. When you think about how to code, it's really, really simple and really fast. As I said, we did it already in the 80s with slow computers. And that saves us a lot of bandwidth. That means when you offer a message, for each offer around, you change the ID to the local ID for that node. But you, of course, doesn't change that number. So that means you never get ID collisions at all, because they're local. So that's probably the better way to do it. And any questions about that? So that actually, I learned it when I programmed teletext systems in the mid-90s, and they had been doing it since the 80s, when the different computers talked with each other. What more to say about that? Something like that. I think we have more kinds of broadcasting. Yeah, of course. In such a system, a node should also perhaps be